After studying this module, you shall be able to know the concept of adsorption and its criteria, distinguish adsorption from absorption, study applications of adsorption, know in detail the adsorption of gases on surface of solid, distinguish Physisorption and chemisorption, and know about different types of adsorption isotherms. Surface chemistry is the branch of science that deals with the phenomena that occurs on surfaces or interfaces, viz. Corrosion, heterogeneous catalysis, electrode processes, dissolution, crystallization, etc. Surface studies are carried out on absolutely clean surfaces. The latter are produced under high vacuum with extremely low pressure of the order of 10 to the power minus 8 to 10 to the power minus 9 pascals. Surface chemistry deals with some important processes of adsorption, catalysis and colloids. Now we shall study about the adsorption process. On the surface of solids and liquids, there occur several residual forces on account of unsatisfied valencies of atoms in case of solids, or non-uniform molecular distribution at the surface of the liquids. Due to the presence of these residual forces, there occurs a tendency of various solids and liquids to attract and retain other molecules on their surface. This is termed as adsorption. Adsorption results in the presence of excessive concentration of substances on liquid or solid surfaces relative to that present in the bulk. Substances on the surface of which accumulation of various substances takes place is termed as adsorbent. The common adsorbent used are silica gel. It is commonly used in laboratories and can be prepared from sodium silicate by the sol gel process. Activated charcoal. It is an effective adsorbent and can be prepared by heating ordinary charcoal to 300 to 1000 degrees Celsius in vacuum or in the presence of steam or inert gas. Finely divided metals like nickel, platinum, palladium, etc. have large surface area and are used in a number of commercial processes like hydrogenation, preparation of sulfuric acid, ammonia, etc. The molecular species, gas, vapor or the solute from the solution that gets accumulated or adsorbed on the surface of the adsorbent is termed as adsorbate. Examples include gases, dissolved substances from solution or ions getting adsorbed onto the precipitate, etc. Now we shall see the difference between adsorption and absorption. The term adsorption can be easily distinguished from absorption. Table shows the differences between the two processes. Adsorption is a surface phenomena, whereas absorption is a bulk phenomena. Adsorption occurs rapidly, that is, the equilibrium is attained fast, whereas absorption takes time to take place. The concentration of substance getting accumulated in the case of adsorption is more on the surface relative to the bulk, whereas in the absorption process, given sufficient time, the concentration becomes uniform throughout the bulk. Examples of adsorption include adsorption of water by silica gel or charcoal, or the adsorption of ink by chalk. And the examples of absorption include the absorption of water by anhydrous calcium chloride or by sponge. Sometimes there may not be a clear-cut distinction between the adsorption and absorption process. In such cases, a non-committal term called as sorption is used. The reverse of adsorption, that is the removal of adsorbed substances from the surface of solid, is called as desorption. Now we shall have a look at the criteria of adsorption. We all know that the adsorption is a spontaneous process. Thus, the free energy change of the system, that is delta G, is negative. When the adsorbate is adsorbed onto a surface, the translational freedom of the latter gets reduced, making entropy change for the adsorption process a negative quantity. This makes the enthalpy change negative for adsorption, with the condition that delta H is greater than T delta S. Thus, the adsorption process is exothermic in nature. This can also be explained by the fact that adsorption process involves attraction between the adsorbate and the adsorbent molecules, and there occurs a decrease in the residual forces acting along the surface of the adsorbent. Consequently, there occurs a decrease in the surface energy which appears as heat. The amount of heat evolved when 1 mole of gas or vapor is adsorbed on a solid is called as the molar enthalpy of adsorption. As the adsorption proceeds, this molar enthalpy of adsorption of the adsorbate goes on decreasing, becoming less and less negative and ultimately becoming equal to T delta S when delta G becomes equal to 0. At this stage, the system attains equilibrium. There are certain exceptions to the fact that the enthalpy change for the adsorption process is always negative. This occurs when the dissociation of the adsorbate takes place and the latter has high translational mobility on the surface. Example includes the endothermic adsorption of hydrogen gas on the glass surface. Hydrogen molecules dissociate into atoms on the glass surface where they move freely. This is accompanied by a large increase in the translational entropy, which is sufficient to overcome the small positive enthalpy change. Now, we shall have a look at the applications of adsorption. Adsorption finds extensive applications in various fields. Water purifiers make use of animal charcoal to purify water. The latter is also used to decolorize cane sugar. Adsorption forms the basis of use of heterogeneous catalysts with the finely divided metals to increase the efficiency of many commercially important processes like hydrogenation of oils, manufacture of ammonia, sulfuric acid, etc. Activated charcoal is used to make gas masks that can be used to adsorb toxic gases and vapors and allow clean air to pass through, especially in places like coal mines. Concentration of sulfide ores by the froth flotation process is based on the phenomena of adsorption. Humidity and moisture control in rooms, bags, and many utility items is done using silica and alumina gels. Colloidal particles of clay in soil adsorb and retain water containing nutrients that is passed to the plants through the roots. Chromatographic separation and purification of compounds used in laboratories and industries is based on the concept of adsorption. Good quality vacuum can be created by adsorbing the last traces of air onto charcoal in a vessel that has been evacuated as far as possible by a vacuum pump. Now we shall see the main types of adsorption. There are two main categories of adsorption that are clearly understood. Number one is the adsorption of gases on the surface of solid, and number two is the adsorption of dissolved substances from solution. We shall discuss each of them in detail. Let us see the adsorption of gases on the surface of solid. First, we shall see the measurement of the extent of adsorption. There are a number of methods available for determining the extent of adsorption of gases on the surface of solid under given conditions. One commonly used method involves determining the pressure of gas at a particular temperature when confined to a glass vessel of specific volume and attached to a manometer. The solid adsorbent is then carefully introduced into the vessel onto which the gas gets adsorbed. After the equilibrium has reached, the pressure of the gas, as noted from the manometer, falls. Using Boyle's law, the amount of gas adsorbed onto the solid adsorbent can be calculated from the fall in pressure, taking care of the volume correction. Other methods of measuring the extent of adsorption include rate integral method, weighing the sample on a precise microbalance before and after the adsorption process, etc. Now we shall see the factors which affect the extent of adsorption of gas on solid surface. The extent of adsorption of gas on the surface of a solid adsorbent depends on the factors. Number one is the nature of the adsorbate. It is observed that temporary gases like ammonia, carbon dioxide, sulfur dioxide, etc., which have higher intermolecular forces of attraction, that is the van der Waals forces, are more soluble, easily liquefiable, and are adsorbed to a greater extent onto a definite mass of the adsorbent under conditions of constant temperature and pressure relative to the permanent gases like hydrogen, oxygen, nitrogen, etc. It is also observed that higher the critical temperature of the gas, more easily it is absorbed. Critical temperature of a gas is the temperature to which a gas must be cooled down in order to liquefy it. Above the critical temperature, the gas shows ideal behavior. Second is the nature of adsorbent. Larger the surface area of the adsorbent, more will be the extent of adsorption. It is for this reason that we prefer activated charcoal over ordinary animal charcoal and finely divided metals as effective adsorbents and catalysts respectively. Number 3 is the temperature. We have already seen that adsorption is an exothermic process. Therefore, as per Le Chatelier's principle, the process is favored by low temperature conditions. This can also be explained on the basis of competition between the two opposing factors, that is, the thermal energy of molecules of gas and the residual attractive forces prevalent on the solid surface. As the temperature decreases, the molecules will possess less thermal energy and will have more tendency to get attracted and retained onto the solid surface of the adsorbent. Hence, greater will be the extent of adsorption. Taking the example of the amount of nitrogen gas adsorbed by 1 gram of activated charcoal at different temperatures under constant conditions of pressure, it can be seen that the extent of adsorption decreases with the increase in temperature. Figure shows the variation of extent of adsorption with temperature. Number 4 is the pressure. The effect of pressure on the extent of adsorption at different temperatures has been shown in figure. It can be seen from the figure that the amount of gas X adsorbed onto a definite mass M of the adsorbent under conditions of constant temperature increases with the increase in pressure and thereafter becomes saturated. The initial increase is supported by the Le Chatelier's principle, according to which, on increasing the pressure, the system proceeds in the direction of decrease in number of gaseous molecules. Adsorption of gas molecules on the surface of solid adsorbent leads to a decrease in the number of molecules in the gaseous phase. Hence, adsorption increases with increase in pressure. Figure shows the variation of extent of adsorption with pressure at different temperatures. The saturation at higher pressures is explained by the concept of fixed number of adsorption sites available on the surface of the adsorbent. Initially, all the adsorption sites are vacant and therefore adsorption increases in proportion with the increase in pressure. As the process continues, the number of available vacant sites becomes small and hence increase in pressure does not cause any further increase in the extent of adsorption. This explains the saturation of the curve at higher pressures. In intermediate pressure range, the increase in the adsorption is not as fast as the increase in pressure. This shows that the process of adsorption is reversible in nature, that is, adsorption and desorption proceed simultaneously till a state of equilibrium is achieved. Mathematically, this can be represented by the equation where M plus S gives Ms, where M is the free gas molecule, S is the active site on the solid adsorbent, and Ms is the adsorbed gas molecule on the solid surface. Now we shall see Physisorption and chemisorption. On the basis of nature of forces operating between the adsorbate and the adsorbent, adsorption of gases on the surface of solids is mainly of two types: Physisorption or physical adsorption and chemisorption, also called as chemical adsorption. If the adsorption of gas on the surface of the solid adsorbent occurs due to van der Waals interaction, for example a dispersion or a dipolar interaction, the adsorption is termed as Physisorption. Since the van der Waals interactions are of long range order and are weak, therefore the energy released in Physisorption is small, of the order of 20 to 40 kilojoules per mole, which is of the same order as that of the enthalpy of condensation of the gas. During the process called accommodation, the gas molecules lose their energy and get adsorbed onto the solid surface. This energy lost either gets adsorbed as vibrations of the lattice, or dissipated as heat. One of the convenient ways of determining this enthalpy of Physisorption is the rise in the temperature of a sample of known heat capacity. Since the values are typically small and hence insufficient for bond breaking, the Physi-adsorbed molecule retains its identity, although it might be a little distorted due to the presence of the surface. On the other hand, if the gas molecules get adsorbed on the surface of adsorbent by forming chemical bonds, ionic or covalent, occupying active sites so as to maximize the coordination number with the substrate, the adsorption process is termed as chemisorption. Since the latter involves the formation of chemical bonds, enthalpy of chemisorption is of the order of 80 to 240 kilojoules per mole. For chemisorption to occur, an essential requirement is the presence of clear-cut affinity between the adsorbate molecules and the adsorbent surface, with distance between the two extending up to 1.5 to 2 angstroms. Chemisorption usually involves the formation of surface compounds. Therefore, it requires sufficient energy to cross the activation energy barrier for their formation. The distinguishing characteristics of Physisorption and chemisorptions are: number 1. Weak van der Waals forces operate between adsorbate and surface of adsorbent in Physisorption, whereas strong chemical forces, usually covalent bonds, operate between adsorbate and the surface of the adsorbent in chemisorption. Number 2. Physisorption is non-specific in nature. Almost all gases show this type of adsorption at low temperatures. However, chemisorption is highly specific in nature, as there has to be a clear-cut affinity between the adsorbate and the adsorbent surface. 3. Physisorption is almost instantaneous, that is, the equilibrium is achieved very rapidly on changing the temperature and pressure of the system. On the other hand, chemisorption is relatively slower, that is, it takes time for the equilibrium to reach. Number 4. Physisorption involves no formation of the surface compounds, whereas in chemisorption, surface compounds are formed on the adsorbent surface. For example, heating tungsten at 1200 Kelvin leads to the formation of tungsten oxide. Number 5. Physisorption is reversible in nature. Desorption is possible by lowering the pressure and raising the temperature, whereas chemisorption is irreversible in nature. Gas once adsorbed cannot be removed from the adsorbent surface by lowering the pressure or raising the temperature. For example, the oxygen adsorbed on the surface of charcoal when desorbed also contains carbon monoxide and carbon dioxide. Number 6. In Physisorption, the enthalpy of adsorption is low, usually of the order of 20 to 40 kilojoules per mole, whereas in chemisorption, the enthalpy of adsorption is high, usually of the order of 80 to 240 kilojoules per mole. Multilayer adsorption takes place at high pressure in case of Physisorption, whereas in chemisorption, since chemical forces operate with short distances only, chemisorption does not extend beyond monolayer of gas molecules on the surface of solid adsorbent. Number 8. Physisorption depends on the surface area of adsorbent. Larger the surface area of the adsorbent, more will be the extent of adsorption. However, chemisorption depends on the number of active sites available on the surface of adsorbent for adsorption process. Number 9. Physisorption involves small activation energy, often less than 5 kilojoules per mole, which is available at low temperature. Therefore, Physisorption is consistently favored by low temperature. However, the activation energy barrier involved in chemisorption is high and is attained at high temperature. Therefore, high temperature favors chemisorption. After the activation energy barrier for the formation of surface compound is crossed, it decreases with the increases in temperature. One of the tools to determine whether the adsorption is physical or chemical is the infrared spectroscopy. IR spectrum of the adsorbent after the adsorption process will be drastically different in case of the adsorption is chemical. Otherwise, it is the case of Physisorption. Sometimes it is possible for Physisorption to pass over to chemisorption at high temperature. For example, hydrogen molecule shows Physisorption on the surface of nickel at 73 Kelvin. As a trend with the Physisorption is the adsorption decreases with the increase in temperature. Therefore, the extent of adsorption starts increasing, attaining a maximum value at 173 Kelvin. Beyond this temperature, the extent of adsorption again decreases. This shows that Physisorption, which is predominant at 73 Kelvin, passes over to chemisorption at 173 Kelvin. This behavior can be explained by the intersection of potential energy curves of Physisorption and chemisorption. Now we shall have a look at the adsorption isotherms. For a particular adsorbate-adsorbent system, the extent of adsorption is a function of temperature and pressure. The graph showing the variation in the extent of adsorption with temperature at a fixed pressure is called an adsorption isobar. We have already studied that adsorption is an exothermic process. Therefore, as per Le Chatelier's principle, adsorption, mainly Physisorption, decreases with the increase in temperature. Figure shows the typical adsorption isobars for Physisorption and chemisorption. If we plot the extent of adsorption as a function of pressure at constant temperature, the resulting plot is called as an adsorption isotherm. Since the extent of adsorption decreases with the increase in temperature, we require an increase in pressure in order to get same amount of adsorption at a higher temperature. Thus, one would generally expect a linear relationship between temperature and pressure. Such a plot between temperature and pressure for a fixed amount of adsorption is called an adsorption isotear. A number of experimental studies have been carried out on the adsorption of gases on different types of adsorbents at different temperature. Based on the results obtained, it is possible to broadly categorize the adsorption isotherms into 5 main categories. Figure shows the 5 main categories of adsorption isotherms showing the amount of gas X adsorbed onto a definite mass of adsorbent M. P0 is the saturation pressure. They are briefly discussed. Type 1. This type of behavior is shown by gases in which the extent of adsorption initially increases with the increase in pressure and thereafter approaches a saturation limit much before the saturation pressure is achieved. This depicts the formation of monolayer of adsorbate molecules on the surface of adsorbent. Any further increase in the pressure does not cause any increase in the adsorption. For example, the adsorption of nitrogen or hydrogen at temperature around -180 degrees Celsius, etc. shows type 1 behavior. Type 2 adsorption isotherms. This type of behavior is similar to type 1 adsorption isotherm, where the extent of adsorption increases with the increase in pressure till a monolayer formation is complete. After the monolayer formation is complete, multilayer adsorption starts with the increase in the pressure. This type of behavior can be explained by van der Waals forces operating between the consecutive layers. Adsorbate molecules in the preceding layer attract and hold on the gas molecules in the next layer. For example, adsorption of nitrogen gas on iron or platinum catalyst at -195 degrees Celsius, adsorption of nitrogen silica gel at -195 degrees Celsius, etc. show type 2 behavior. Type 3 adsorption isotherm. This type of behavior occurs when multilayer adsorption starts even before the monolayer formation is complete. There is no way to distinguish monolayer formation from multilayer formation, and there occurs a continuous increase in the extent of adsorption with pressure. For example, the adsorption of bromine or iodine vapor on silica or alumina gel at 80 degrees Celsius falls under this category. Type 4 category. This is a duplication of type 2 adsorption isotherm. First, the monolayer formation starts, then it completes, and then the multilayer formation starts, and thereafter it gets completed. This behavior has been explained by the phenomena of capillary condensation, in which some of the adsorbate molecules have a tendency to get condensed within the narrow pores of the adsorbent at pressures even lower than the gas saturation pressure P0. For example, adsorption of benzene vapors on silica gel at 50 degrees Celsius show type 4 behavior. Type 5 behavior is erratic and does not fall in any category, and therefore is separately classified as type 5 adsorption isotherm. For example, the adsorption of water on activated carbon at 100 degrees Celsius falls under this category. Now we shall summarize what we have learned in this module. Adsorption is a tendency of various solids and liquids to attract and retain other molecules on their surface. It's a surface phenomena and is different from absorption, which is a bulk phenomena. Adsorption is a spontaneous process. The enthalpy of adsorption is usually negative with the condition that delta H is greater than T delta S. Adsorption finds extensive applications in various fields. Adsorption of gases on the surface of solid and the adsorption of dissolved substances from solution are the two main categories of adsorption that are clearly understood. On the basis of nature of forces operating between the adsorbate and the adsorbent, adsorption of gases on the surface of solids can be classified into two types, Physisorption and chemisorption. An adsorption isobar shows the variation in the extent of adsorption with temperature at a fixed pressure. If we plot the extent of adsorption as a function of pressure at constant temperature, the resulting plot is called an adsorption isotherm. It is broadly possible to categorize the adsorption isotherms into 5 main categories.